Hello everybody, welcome back. Today in geometry we will be looking at section 7.6, what is known as the first minimum theorem and also the triangle inequality theorem. So there are two big things that we need to get out of this entire section. So let's go ahead and talk about them so then that way you can see what they're actually for then. So the first one is what is known as a the first minimum theorem, which is a very minor one, but it's kind of nice to know. And then the triangle inequality theorem, that's going to be the big one that we're going to be using for quite a while from here. All right, so here's the first part then. The first minimum theorem. It says in the first minimum theorem the following: the shortest distance from an external point P to line L is the perpendicular segment. So on the picture on the right hand side, what I'm trying to say is that if P is a point that is not on L and they are all on the same plane, which they should be because you have a point and a line, then the shortest distance is supposed to be the perpendicular that's located right there. Any other distance that I draw from here to here or from further out, those are going to be bigger than the perpendicular. So let's go ahead and see if we can do like a quick proof of this one. So here we're going to do the following below. I'm going to go ahead and say let A be the point on line L such that PA is perpendicular to L at A then. So we're basically going to introduce the perpendicular segment. So let me go ahead and erase all of this right here. So then that way you can see the picture a little bit more better. So here is point P, and I am going to use the point plot theorem to go ahead and introduce point A on line L such that you have the perpendicular. Next, after we create that perpendicular, we're going to go ahead and say let point B be any other point on line L. So then that means that over here, maybe to the right hand side of it, I'm going to go ahead and introduce any old point B. So the triangle might be bigger or smaller depending on how you draw it, but nonetheless, it's always going to be somewhere on the right. Technically, it could also be somewhere on the left, doesn't really matter. Now, what you'll notice here is that we have a right triangle, PAB, because of the right angle that's there. And in a right triangle, if you remember, the other two angles right here, they have to be acute, okay? So here, let me just kind of write that down. In any right triangle, okay, the other two angles are acute. And that is to say acute meaning that is less than 90 degrees. So therefore, what that means is that the measurement of angle A is greater than the measurement of angle P, or we can actually say that the measurement of angle A is going to be greater than the measurement of angle B. And right there, that now allows us to set up what we did in the last section, which talks about if we have some sort of comparison of the measurement of the angles, we can look at their opposite sides. In the first case, we're going to say that since measurement of angle A is greater than the measurement of angle P, then that gives us that PB is going to be greater than AB. And that right there is not exactly what I'm looking for because we don't care about the line segment AB. So we'll go ahead and cross that out. It's nice to prove it, but we don't really need it. But in the second case, now this one is the where it's interesting then. Measurement of angle A is greater than the measurement of angle B. So that means that PB is going to be greater than PA. And right there, that is exactly what we're looking for. The side that is the quote-unquote hypotenuse is always going to be bigger than the opposite, which is the perpendicular right there. And actually, you know what? Now that I think about it a little bit more, if we look at this as a whole right here, this is basically saying that in a right triangle, the hypotenuse is always going to be the longest side, which hopefully you know already by now. Okay, so the hypotenuse is always going to be the longest side in a right triangle. All right, now let's go ahead and extend this a little bit further. Okay, let's go ahead and go a little bit further with this. And let's say this time around we have a just, any old triangle, not necessarily a right triangle. This one is called the triangle inequality theorem. So if you want, you can go ahead and, write in short, triangle inequality theorem. That might be a little bit easier to write down. Okay, just kind of like SAS, ASA, and so forth. All right, but anyhow, in the triangle inequality theorem, it basically states that the sum of any two sides of a triangle will always be greater than the third side. So that is to say, if you add up any two sides of the triangle, it'll always be greater than the third. So as a restate, I wrote it down here, AB plus AC is going to be greater than CB, and AB plus CB is greater than CA, and also CA plus CB is greater than AB. So all those three things we basically have to prove. And even though it looks like it's a lot, it's actually not that bad, okay? So here is what we're going to do. Now, for this proof right here, what we're going to say is the following. You'll notice that in the first two equations, they both contain AB. Okay, they'll both contain AB. So why don't we go ahead and say that assume that AB is the longest side. Okay, so assume that AB is the longest side. And I can always do that because for any triangle, there will always be a longest side. And it doesn't matter how you set up those three equations. The longest side will always be added with something. It's going to be greater than the third side. So anyhow, we're just going to go ahead and say that assume that AB is going to be the greatest side then. If AB is the greatest side, then we're pretty much done because you can see that if you have the largest side, right, plus the another smaller side is going to be greater than any of the other side. The largest side right here plus any side is going to be greater than any of the other side. Now, all we have to care about is actually just this last case right here. I just need to prove this guy, and then we're pretty much good to go. So, keeping in mind that AB is still going to be the largest side, that's what I want to prove. Well, let's go ahead and do the following then. Let me go ahead and draw a line segment right here. And I'm going to go ahead and use kind of like, my theorem, the first minimum theorem that we just had over there. I'm going to go ahead and introduce a point D on AB such that CD is perpendicular to AB. So basically, I've just created a perpendicular CD to AB right there. Now, according to the first minimum theorem, right, the previous one that I had right there, I can say that CB, which in this triangle over here, is going to be greater than DB. Okay, so by the first minimum theorem, I can say that CB is going to be greater than DB. Remember, CB is going to be the hypotenuse in this case, so therefore it's bigger than any of the legs. And similarly, if I say by the first minimum theorem, I can also say that CA on the other triangle over here, which I will go ahead and, color for you right there. CA is going to be greater than AD because once again, CA is going to be the hypotenuse. Well, taking what I have right there with those two equations, if I add them together using the addition property of inequality, you'll notice that we're going to get CB plus CA, which is what I want over here to prove, is greater than BD plus AD. And BD plus AD, according to the segment addition, that is the same thing as AB right there. So by substitution, then that means that in the very end, CB plus CA is greater than AB then. And there you go. That's going to be our proof. All right, so now let's go ahead and look at some numerical examples to see why this is once again relevant. So here in this first one, not a proof problem, but it's just going to be something, that will hopefully connect everything that you just learned to make it make sense. I want to know, is it possible to have the following triangles with the following lengths? So here you can see I have three scenarios. In the first case, I have 8, 20, and 15. So according to the triangle inequalities, we can set up a whole bunch of things, right? We can say 8 plus 12 is greater than 15, which is true. 20 plus 15 is greater than 8, which is true. And finally, 8 plus 15, which is greater than 20, which is true. But the easiest way to verify that this is true is always take the two smallest side. Always take the two smallest side, which in this case is going to be 8 and 15. Now, if I add those two together, according to the triangle inequality, it should be greater than the largest side, which is going to be 20. And if that works out, then we're pretty much done. Okay? So once again, all you have to do is just take the two smallest side, add them together. And if it's greater than the third side, then yeah, this triangle is definitely going to work out. Let's look at the second case over here. 3, 4, and 5. Oops, which I just erased. So 3, 4, and 5. So we're going to take 3 and 4. We'll put them next to each other, add them together. Is it greater than 5? The answer is yes. So yeah, that actually works out then. Now, let's look at the third case over here. 7, 3, and 10. If I take 7 and 3, add them together, is it greater than 10? The answer is no. So that means that this triangle right here, it is not possible. Nor if I did this. What if I had, like, say, a 1, 2, and 5 triangle, right? If I take 1 plus 2, it is definitely not greater than 5. So that means that triangle is not going to be possible. So once again, that's probably the fastest way to use the triangle inequality theorem to prove that your triangles with certain sides are going to be available in this case, or possible. Okay, now here's the proof of using the triangle inequality theorem. Here, let's see what it says then. Prove that the sum of the medians is greater than half of the perimeter. So you can see in the picture right there, we have triangle ABC, and I'm going to make it so that D, E, and F are going to be the midpoint. So if you want, you can technically go ahead and make a dash right here to indicate that you have a midpoint. But as a restate, what we have is I need to show the following. BF plus C plus AD is greater than 1/2 of, in parentheses, AB plus BC plus CA. Now, I'm not going to lie to you guys. I actually sat here for about 20 minutes to look at this proof and see how is it going to be written out, because there are a lot of ways you can write it out according to the triangle inequalities, because if you go back again to my theorem right here for triangle inequalities, there are 3 different combinations. So the question is which one to actually use. So here is something that kind of helped me out into coming up with my conclusion. Since I'm trying to prove that the sides, right, the medians are greater than the sides, then I basically need to somehow come up with something that says BF is greater than something. I need to have something that says EF is going to be greater than something. And then I also need something like, say, AD is going to be greater than something. Well, in terms of what those somethings are, that's where I kind of like, kind of rub my head a little bit. But here's what I came up with. Now here, let's go ahead and focus on this triangle over here. I didn't draw the other, what's that called? Medians just yet, because I don't want it to like, be too confusing in the triangle. But there it is. That's the triangle that I'm focusing on. In that triangle, according to my triangle inequality, I can say the following. I can say that BF plus 1/2 of AC is going to be greater than AB. Okay, BF plus 1/2 of AC is greater than AB. Now, here is AB over here, which I'm sure you can see. Here is BF over here, which you can see. And the third side is supposed to be AF. But you'll note that what I wrote was 1/2 of AC instead, because I don't want to introduce more variables if possible. I want to relate it to, all my other equations if I can, okay? Remember, in algebra, what you want to do is minimize the number of variables that you have, so then that way you can solve for it. It's not good to make so many variables. All right, so I'm going to go ahead and try to get rid of F over there. But nonetheless, let me just go ahead and write that down one more time. BF plus 1/2 of AC is greater than AB. Okay, now what I'm going to do is I'm going to go ahead and focus on a different triangle. So let me go ahead and erase this guy right here. And let's look at another median in this case. So the other median is going to be EF. Oh, sorry, not EF. It's going to be EC. So I kind of made a small little mistake right there. Okay, so EC. So that is going to be this guy over here. And now I'm going to go ahead and focus on the triangle that is underneath, that is over here, okay? Just to kind of look at it as kind of like a rotating counterclockwise. And in that triangle, here's what I can say. EC, right, is going to be added with 1/2 of AB, not looking at BE, but, instead looking at AB as a whole, is going to be greater than the third side, which is going to be BC. Okay, so hopefully you guys can see that. And finally, let me go ahead and draw the last one in this case, which is going to be AD over here. Okay, so in this one, similarly, what I can do is say that AD plus 1/2 of BC is going to be greater than AC. And all of these, once again, is because of the triangle inequality theorem. Okay, looking at what I have, looking at what I want, the first thing that comes to mind is I probably want to add up everything then. So by the, what's that called? By the addition property of inequality, then I can say that BF plus EC plus AD, because that's what I was going for. And then plus all of these extra stuff, 1/2 AC plus 1/2 AB plus 1/2 BC is going to be greater than, and let me go ahead and erase this API on the side over here, the right hand side, which is AB, which is going to be BC, and then also it's going to be AC. Add them all those together. Hey, if you notice, what we have now is that we have AB on both sides right here. Okay. We also have a BC on both sides over here. And then finally, we have AC on both sides over here. So maybe what we can do is we can subtract over. So once again, let me just kind of write this out. This was by the addition property of inequality. And I believe the last part, which is basically going to be the last step of the proof, is to subtract over to the other side. So then that means that if I have AB minus 1/2 AB, that's going to be 1/2 AB, because 1 minus 1/2 is 1/2. Then plus 1/2 of BC, and then also plus 1/2 of AC. So this is by the subtraction property of inequality. And right there, that is basically what we want to prove. So there it is. We're going to be done then. So I have to warn you guys that with these proofs, with the triangle inequality theorem, it's going to get a little frustrating because there are a lot of combinations that you can write. So your job is to basically kind of decipher which one is the best one to take. And the question is why? Hopefully after a while, once you get used to it, then you're going to get more, become more of an adept, and you'll be able to see it immediately versus like, sitting there for like 20 minutes like I did. All right. Well, thank you so much for watching. I will see you next time. Have a good day. Bye.